we are looking at the transient response specifications. What are the transient response? Like if you have a response, time response of a system of the plant. So CT is the control variable. So these are the definitions. The time to reach the input, the set input, it varies for transfer function to transfer function, system to system. But we have made a definition that 63% is the time, 63 from 0 to like 0.63. That time is about the time constant. Time constant. Time to reach the set value is 63% of set value. And then time, the peak time is the TP when the first peak comes, and this is the maximum overshoot. That after the set value, the system, like the mass still does not stay there. For example, the new position is 2 centimeter, but it goes up a little bit above this, beyond this value. So it then comes back and then goes forward and then stays. The final position is about this position. So this overshoot, it should be avoided to most of the cases, but there is a trade-off. To have the faster response, you might have to face this maximum overshoot. And the rise time is the time for the system to reach from like 0.1, like 10% to 90%. So we take the 0.5, means 50% of the, sorry, this is the delay time, 50%. So the rise time is this range from 10% to 90% of the set value. And TS is the settling time, which is 4 times the time constant. Settling time is 4 times the time constant. This is tau is time constant. And what is time constant? This is equal to 1 over zeta omega n. So let's see, these are the definitions here: delay time, rise time, peak time, maximum overshoot, settling time. So you can read them, and we will show you in the Simulink modeling how to find out this. So this is an example. These are known as the transient response specifications, and there is an example given here in our book for this shaft which is rotating and torsional vibration, and it has some torsional damping, and there is no spring here. Torsional damping is there. There is a gain value here. So you find this one over here. So the transfer function is this one. This is our actual transfer function, and this is our standard transfer function. You have to compare the actual with the standard in order to find out what are the unknown parameters. So omega n comes out to be k square root k over j, which is this part, like numerator is omega square. You just take the square root on both sides, and the zeta from here is not that difficult. You just compare the s terms in the denominator. B over j equals 2 zeta omega n, and here we know that omega n is square root k over j, and zeta is equal to b over 2 j omega n, and b over 2j square root k over j. And if you do the math, j is power 1, here j is 1/2, so you get b over square root 2kj. This is the same thing which the book has written down for the zeta, how to find the zeta of the torsional vibration, which is the damping ratio. And that's it for transient response. This is an example which I've copied pasted here to show you how to find out the rise time with the formula. This formula have been given in our book Ogata with the equations. Omega is the damped vibration, maximum overshoot can be found through the graph and so on. So now settling time is the time 4 times the time constant. Time constant is given from the plot time response, like 60% of the set value. So these are the unknown the transient response specifications you can find out.